Alright, this is the last video for the chapter. We're going to look at 1610 and 1611. And 1610 talks about acid-base behavior and what has to do with their structure and how they're put together. So, any molecule containing a hydrogen is potentially an acid, but there are many molecules that have no acidic properties that have a hydrogen with them. And there are two main factors that determine whether your molecule with an XH bond, meaning the X meaning anything, Cl, ClO, SO4, whatever you have there, will behave as a Bronsted Lowry acid. There are two things you look at: the strength of the bond and the polarity of the bond, and they kind of actually go hand in hand there together. So the first we're going to look at is binary acids. So let's remember that binary means two things. So we're looking at not something with an oxygen, a chlorine, and a sulfur. We're looking at just like HCl or H2O or H2S, something with just two things. Alright, well there are kind of two trends here as you go across the period or as you go down the group. And so here's a chart and we're going to explain how and what this chart is saying. So the first thing deals with, okay, if you're looking at things that are in the same group. Okay, so we're going down the periodic table. Alright, as your size of X, which is whatever the H is attached to, increases, which means we're going down the table, remember. Okay, the strength of your bond goes down. The strength goes down because they're getting further apart, so the H to whatever is connected to is a lot further apart than then higher up on the table where the H and the whatever it's connected to are closer together. Well, since they're further apart, the strength of your bond decreases, which means that they are easier to take apart. And if we're talking about acid strength, acids are all about dissociating, and the stronger the acid, the more it can dissociate, the more it does not want to stay together. So if it's easier to break apart, meaning it doesn't want to stay together, that means you have a stronger acid. So the acidity increases down a group. That's why you have those arrows there. The red one says increasing acid strength as we go down from CH4 to SiH or HF to HCl. HF is actually a very weak acid. Things like HCl, HBr, and HI are much further apart, much easier to break apart, therefore they're a much stronger acid. Okay, so there's the group trend. We're talking about now the period trend, where we're going across. Okay, here we're going to look at the acidity increasing as the electronegativity increases. Okay, so what we're looking at here is that my bond is more polar. The bond's more polar. The electrons spend more time around whatever is connected to the H. So again, the bond is weaker. The H basically doesn't want to be attracted to it at all and will actually leave, attach to water or attach to something else, and it's easier to break. So as you go across the periodic table here, we're looking at comparing like H2S to HCl. Okay, same period. HCl is a much stronger acid than H2S. Okay, Cl is more electronegative. It wants to take those electrons pretty much from chlorine or from hydrogen. Hydrogen then is left kind of out by itself, so it's pretty much an H+, which will easily bond to any water that goes by that H+ on the chlorine. So as your electronegativity goes up, my bond's more polar and my acidity increases. Those are for binary acids. If we look at what we call oxy acids, remember those are things that have oxygen with them now. And now we're looking at a chlorine or an iodine, an O, and an H. So I've got some numbers of oxygens connected to my H. Okay. Well, you got kind of two things to look at. If your X has a high electronegativity, meaning it's going to take those electrons and kind of take them next to it. So chlorine and iodine have higher electronegativities. And notice how these arrows here mean that these electrons are moving, shifting towards the chlorine. Since they're moving or shifting towards your chlorine, okay, the COO, in this case, or the IO bond, so the XO bond, okay, is stronger. Pretty much it's covalent for the most part. And H+ is lost because you're going to break apart your bond here because all these electrons moving this way, so it's kind of the same thing as the last time I was saying with polarity. This H is essentially an H+ because the electrons move way away from it, so the water that comes by here is going to very easily attach to that H+, and that's going to take it and it's going to go. Okay. Now, if you have a low electronegativity, so if I have an example that I don't have here, if you have, for example, CaOH, okay, this bond here is very weak. It actually acts like an ionic bond, so it's going to be easily broken in water. So what happens is now you break here, and now I've got a Ca and an OH. I don't have an acid. So if you have a low electronegativity, then your OX bond is ionic and broken in water, leaving your cation and an OH, which is not an acid. That's actually then a base. The last thing we're going to look at here with these oxy acids is if you flip over the page, the top, okay, now what if I have multiple oxygens connected to my chlorine or my phosphorus or my sulfur or something like that? The more oxygens you have attached to your center, the more acidic it is. Okay? Perchloric is a very strong acid, so is chloric, but these two, chlorous and hypochlorous, are not. And the reason being here that your electrons get pulled away from the chlorine. Okay, the more oxygens you have, the more it gets pulled this direction and away from the H. The more easily it is to break that H off, the more acidic it is. So the more oxygens you have, the more acidic it is. It's all about how your electrons get pulled here with your polarity for the most part. So these electrons are getting moved towards the chlorine, towards all these oxygens that want these electrons, and not near the H. So the H is very easy to lose. So let's look at an example here. Arrange the following compounds in order of increasing acid strength. We have ASH3, HI, NaH, and H2O. Remember again, okay, a higher electronegativity is pretty much going to result in a stronger acid because you're leaving that H off there by itself. HI is the strongest acid. I has a very high electronegativity. It wants the electrons around it. It's going to leave that H off by itself. So HI is our strongest acid. So when I look at things that have the lower electronegativities, on the other end, that's going to be this guy, sodium, all the way on the other end. So I'm going to have NaH, because this is a very low electronegativity. It's actually going to give up electrons. Okay. Now then we've got ASH3 and H2O. Okay. ASH3, AS is going to have a lower electronegativity than O. O is way closer to fluorine. So we're looking at ASH3 and then H2O. And then my strong acid of HI. Okay, now we're going to look at the next problem, which deals with oxygens. Okay, in order of increasing acid strength, I have H2SO4, H2SeO3, H2SeO4. Okay, well, we got increasing oxygen numbers between these two. Well, the more oxygens you have, the stronger the acid. So, H2SeO4 is going to be stronger than H2SeO3. The question becomes, where does H2SO4 fit in here? Well, S is way more electronegative than Se, so S is going to be the one that's going to pull the electrons more closer to it. So now we're looking at H2SO4 being the strongest acid of that group, and it is a strong acid, which would also have maybe put that on the end. Okay, last section here. We're talking about a Lewis acid and a Lewis base. This is like our last definition of an acid and a base. This is the most general definition. This one came about because somebody realized that there were a few things that were actually acting as an acid and a base but did not fit that Bronsted-Lowry when we're talking about protons accepting or donating. So they made these definitions. A Lewis acid is an electron pair acceptor, and a Lewis base is the electron pair donor. So a Lewis base can donate its electron pair to something other than hydrogen. Because there are things that act as acids that do not have these hydrogens. So here we're looking at N is donating its pair of electrons to boron here. So this would be my Lewis base, boron would be my Lewis acid. Okay, let's look at the example. All right, I have Ni and NH3 making NiH NiNH3. And so I've got an Ni, and I've got NH3. And NH3 has those lone pairs. So N here has my lone pair. It's going to donate it to nickel. That way nickel can attach itself to the NH3, which is all that happened there. Okay, so that would make NH3 my Lewis base and Ni my Lewis acid. Okay, I've got H plus water yielding H3O plus. Well, water is my one with the lone pair, which means it's going to be my Lewis base. It's going to donate its one pair to H, which makes this a Lewis base and makes this a Lewis acid. Also, look how I could also use the Bronsted-Lowry definition. It would be the same here. H plus is obviously the acid because it's donating itself to something else. So the definitions also work for things that you would normally classify as a Bronsted-Lowry acid or base.